So here we have a related rates calculus problem that says a spherical balloon is being filled with air at the constant rate of 2 centimeters cubed per second. How fast is the radius increasing when the radius is 3 centimeters? So let's think about what this problem means. I'm going to first draw a little balloon, and because I'm a horrible drawer, I'm going to use this little tool. So here's our balloon, and it's being filled with air at a constant rate of 2 centimeters cubed per second. So let's think about what that kind of unit means. If it's being filled with air at a constant rate of 2 centimeters cubed per second, centimeters cubed is a unit of volume. So because we have a unit of volume that's divided by a unit of time, that would be a unit of volume per time, or we can think about that as a volumetric flow rate. Volumetric flow rate. And the way we can write that in terms of derivatives is we would write a volumetric flow rate as the derivative of volume with respect to time. And we often write that as dv dt. So the d's mean like the change. So it would be the change in volume divided by the change in time. Another way to write that would just be v prime, but we would often write that explicitly as a function of time, because that volume is changing with respect to time, since it has an amount of volume per an amount of time. So as we are filling this spherical balloon with air, it is getting more volume of air into the balloon, as well as the balloon, because it's a balloon and it has a stretchy outer surface, it would be getting to be a larger balloon. So the volume would be changing and the radius of the sphere is changing. So those are our two things that are changing in this problem. So we need to write a formula that has to do with the volume of a sphere. So if you look up the volume of a sphere formula from geometry, its volume is equal to 4/3 pi r cubed, or that's the most common formula that I'm familiar with. And we did want it in terms of volume and radius because the problems, or the things that were in the problem were in terms of volume and radius. So this is a perfect formula. It only has volume and radius, so we don't need to do any getting rid of other variables. We don't have 3 total variables, just 2. So once we have this formula, we want to find something that has to do with how fast is the radius increasing. So just like dv dt is a volumetric flow rate, the change in the radius we could write as dr dt. This is how fast the radius is changing with respect to time. So since both volume and radius are variables that change over time, when we take the derivative of them, we need to use the chain rule and multiply by the derivative of the inside function, which is like the time function. So when we take the derivative of v, we'll write it as dv dt, because it is a function of time. Because the derivative of volume, the derivative of any variable, like the derivative of x, is just 1. So this derivative of v would just be 1, but then we need to multiply it by dv dt, since it is a function of time. Let's take the derivative of the right side as well. We'll take the 3 and bring it down. That would multiply by the 4 to make 12/3. And we're using the power rule here, by the way. So we bring down the 3, multiply it, and then the pi is just a constant. And we need to subtract 1 from the exponent. 3 minus 1 is 2. But because the radius is also a function of time, we need to use the chain rule and multiply by that dr dt. So every time you take a derivative of a variable that changes over time, we need to multiply by that dr dt, or whichever variable dt. Okay, so simplifying a bit, we know that dv dt was given in the problem as 2 centimeters cubed per second, so we can plug that in as a 2. And then 12 divided by 3 is 4, so 4 pi. Also, since we've taken our derivative, we can plug in like things that are happening at this instant that we're interested in, which is the radius is 3 centimeters. So we'll plug in 3 for our r, and then times dr dt, we'll leave that because we're looking for how fast the radius is increasing, which is our dr dt. That's our change in radius with respect to time. So simplifying a bit more, we have 3 squared would be 9, and 9 times 4 is 36. So 2 is equal to 36 pi times dr dt. And then let's divide both sides by 36 pi to solve for the dr dt. So the 2 can cancel out with we can divide out by 2 on top and bottom to make 1 over 18 pi is our dr dt. And we can plug that into our calculator if we're looking for a particular number. But notice that our dr dt we got as a positive value, which confirms that our radius is increasing. So that would be our answer. 1 over 18 pi is our dr dt. So I hope this video was helpful for you. If it was, please like the video and share with anybody you think might find this information useful. Also, subscribe to my channel to see more similar videos of homework help. Feel free to leave any comment that you have. If you have a question about this video or a question of another homework problem that you would like to see worked out, feel free to leave that in the comments, or also my email is down in the description box if you would like to send me a picture, if that's easier than leaving a comment. Thanks for watching.